it was literally ridiculously kind in the sense that it'll be downhill. I think in an autobiographical way, it might be Mac. It's probably important for me to say that I don't do it anymore, but I used to probably read, I don't know, between 100 and 200 magazines a month, mostly sitting on airplanes and waiting for airplanes. And there was a time when all of a sudden, all the fashion magazines had this image of Bill's sails with a Prada logo over it. And I don't know which America's Cup it was, but one of the cups where Prada sponsored a team, they used a lot of Bill's imagery in their advertisements. And when I was a kid, I used to do a lot of sailing. I mean, I had a kind of I still have great father, and he kind of retired early and spent a lot of time on the water when I was a kid. And so I sailed and sailed and sailed and then gave it up. And it was really seeing the material that got me back into sailing. And it was also seeing that material, and I know Johan and I talked about it, because, I don't know, Johan's always been fashionable, but he was also aware of those images. And we both said, this is an incredible material for architecture. And Renzo Piano thought that. I would say a big number of architects saw the material and said, we got to get that into buildings. So maybe tonight, now 10 years later, I'll try to explain some of the reasons I was seeing things in it. And I think it's important when people talk about intuition and things, it usually means, at least in English, how a person feels. And I actually have no interest in that kind of intuition. But I know I saw in those sails some structural principles, material principles, construction principles that I didn't understand, but that I knew were going someplace. And so, you know, I did everything I could to go meet Bill and went and saw his factory, and now 10 years later, we're doing some things together. So I just think for students especially, it's important to keep your eyes open, and when you see a thing, you know, take 10 years to patiently chase it. So anyway, it was really seeing that imagery that got me interested in composites. And I'll try to talk a little bit today about how different your design attitude has to be when you think about composites. And because there are probably people here other than architects, this may not be, but architecture is particularly hostile to composites. We don't tend to understand composites because the way we think about things is about tectonics. So tectonics, which in Germany you understand better than in any other nation on earth, you celebrate details and you celebrate connections and you celebrate the mechanical attachment of parts. So it's not so much the surface that architects are interested in. The architects are interested where two surfaces come together. And that point of connection is usually where we locate our details and where we celebrate the details. We also tend to want to celebrate structure in and of itself, where in composites, the structure is everywhere and nowhere. We like to have structure be expressed as a frame or a pattern or a grid. And we also like hierarchy of systems. So if you have a structural frame and a cladding and an interior, we like to celebrate the fact that those are disparate things, and we like to celebrate how they relate to each other intricately. So that's what we do, and all of that is hostile to a real understanding of the principles that Bill just talked about. I mean, whoever asked that question is on the right track. I mean, in our lifetime, there will be a boat which is one monolithic, semi-flexible thing. There won't be a mast and a sail and a hull. It'll be just one big semi-flexible shape. So Bill and his people are on a mission to eliminate everything we love about architecture and make it microscopic and make it layered and pull it all together in a monolithic, intelligent way. So that's the program, I think. So this is a tectonic, I mean, it's a Semper drawing of a primitive hut, but you can see these qualities of celebration of structure. The reason I used it is because it's about textiles, but this is an architect thinking about textiles. So it celebrates the structural frame, it celebrates the knots that tie the frame together, and then it layers a skin over that. And I mean, right now, architecture is particularly interested in layering lots and lots of skins. So the one thing I would just warn you about is computer technology is letting us make more and more complex geometry, but when it comes to building it, we tend to try to celebrate that geometry. So we would put all of our structure on the lines of geometry, just in a finer, more technical way. So for me, Johan mentioned the church. I mean, this is a tectonic project. I mean, this is 15 or 18 years old, but you can see that the outer skin, the structure, the interior cladding, they're all hierarchical layers. They're very intricately connected. What I was proudest of, or am proudest of, is that this was a very digital project in the sense that every dimension and every panel was unique. It was all controlled and interrelated. It was very rhythmic in the sense that all of these different dimensions related one to another, but it was super tectonic. And it was really about celebrating structure and celebrating connections. And that's a thing that I'm not so driven by anymore. So what I thought I would do is bring some examples of just general composite work, but without the sensibility, and talk a little bit about those, and then end talking about some of the things that Bill and I have been doing together. The first principle of this kind of a composite construction is moving from mechanical connections to chemical connections. And I know I've always been impressed when somebody at BMW tells me that my car doors are glued to my car, that the bolts are just there for placement, but that actually the car is all glued together. And it's true now, I go all over my car, go look at your car, you'll find very few mechanical attachments. It's really held together with glue. And also when you go on a construction site, everything's mechanically attached, and then all the people come with the glue and the silicone and the caulking, and there's a lot of glue in our industry too. So I've been trying to build things with no bolts, no nails, no screws, just all glue, or in this case, no glue at all. This was at the same time that we did the carbon crystal sales. HSBC Bank asked me to do a pavilion for their collectors that could get shipped around easily. So we came up with this flat pack system where really in a day, 2 or 3 people could take things off of a van, not even a container, and put all of these elements together like a hex, like a grid, or like a core. And then we would put the windows and the openings through it by just thinning that core down so you'd get holes in it. And we didn't even actually have to bolt it to the ground. So there's absolutely no connections there other than friction connections. It led to the index pavilions, which opened maybe 6 or 7 months ago in Copenhagen. And it's the biggest design award in the world now, and they have 80 objects that they display, and the pavilions go around to over a dozen venues in a year. So these pavilions will travel maybe 30 to 50 times across an ocean. And they came to me and they said, look, the budget for the pavilions is a couple €100,000, and they have to be holding this many objects. You don't go inside them. They have to be vandalism proof. They have to generate their own energy so we don't have to run electricity to them. And they have to fit in a minimum of 12 shipping containers. And I said, well, what's your annual budget for shipping containers? And they said, €500,000. And so I said, well, if I could get all 9 of the pavilions in one shipping container, can I take that 450,000 euros? And they said, yeah. And I said, okay, so we're going to build these in carbon. So really what we did is we saved them a lot of money just by making these things light and compact and strong. So then the second thing, I have to say, they came to me and they said, well, you're going to build it out of wood because we're Danes and Scandinavians and we think wood is sustainable. And so we actually did an analysis of how sustainable it would be to build them all in plywood versus building them all in carbon reinforced plastic. And it turns out we were using so little material and the transportation was so bad, using so much petroleum and energy, that actually the carbon footprint of doing them in carbon was better than doing them in wood, better than plywood. So anyway, a lot of these materials Bill has talked about, they're super sustainable. They're horrible as a material themselves, but you don't build a building that weighs thousands of tons out of them. You use hundreds of pounds. So anyway, if you look at the big picture, they get really interesting in this day and age with the concerns of architects and clients and culture. Anyway, so these have already been, they split them up. They've been in over 10 cities already. I think, I don't know where Resor is, but 5 of them are in Resor right now, and then they'll go to Singapore. Anyway, and these also flat pack. The reason they're compact is you take them apart, you stack them all up, and the boxes are composites in the sense they're 2 aluminum skins on a plastic core, and we just score through one side of them so you can fold them. And so even the vitrines unfold flat and get stacked, and then we fold them back together. And those, I have to say, have screws rather than Velcro. But everything else is completely non-mechanically connected. The boxes actually stabilize the grid. That's them in Singapore. That kind of a language of construction has influenced larger scale construction. This is a pavilion across from LACMA in Los Angeles. We're still working on, where the trellis of it is not a weather enclosure. It's actually just there for shade. So that's a very lightweight and potentially composite construction. It could also be aluminum. I mean, I think at a certain scale you find out the 2 things are very similar. But in terms of its stiffness and rigidity, again, it's one of these kind of flat pack type structures. The other thing I started doing with plastics is I noticed a lot of my colleagues were fascinated with masonry, like Office DA, and I was at the ETH for a while, and when I left, Matthias Kohler, who was my assistant then, moved on to these stacking masonry logics, and I thought, that I really had no attitude, not about bricks, but about modules. So I thought I would try to design a plastic brick, like a very lightweight, hollow plastic brick. And I thought that brick, could be like a, kind of a convex pop culture type shape. And as I was doing this, I was looking at my kids. Maybe let me see if I've got, who were on these things. And every 6 weeks, we'd get one of my kids some big rotomolded plastic thing, and we'd get attached to it and they wouldn't. And so I started to develop like a whole garage full of sentimental plastic toys. And I had the idea to make a wall out of these toys as a kind of a test of this brick concept. So I scanned a bunch of these toys and programmed them in a computer and was, built a model and had the guy over who could cut them. And he said, well, why don't we just industrialize this process and we'll sell them through my company, Panelite. And so I ended up inventing my own brick. Bill, was that your laser pointer? So the principle of the brick was just that I would put 3 lobes on it, so you could always nest one end of it into the back side of another one. And then by staggering them half a module, you could always put the thick section of one on the places where two of them intersected. So they would always go like this, and they could always stack up. So we designed that brick. We actually built the tool in my office, molded it in plastic, and then this is the robot of a company called Minimalist, which is a specialty fabricator in Los Angeles. And we would take each one of those bricks and find their intersection, where this one intersects that one, for instance, and we would cut away a hole in one brick, then leave the rest of it whole. And then in a very labor-intensive way, you stack all these things together and they interlock, and then you weld them together with heat, so they become one monolithic surface. So, and we've done, I don't know, maybe close to a dozen of these for interiors. SIARC asked me to do one as an exterior, and for a shape, I just made a giant version of the brick shape. We did realize that you need a jig as you get something this big, because you can imagine like 30 or 40 students with all these numbered bricks starting at a different area and stacking them up and welding them, that when they came to meet, there was a lot of inaccuracy. So at this scale, the intricacy of the components really starts to need a new method of precision and control. But, I mean, you can see there's some pretty significant cantilevers and everything in this thing. Then Aaron Betsky, who was the director of the Venice Biennale, asked me to bring this pavilion to Venice, but then his Dutch graphic designers did a blob wall signage scheme. Honestly, they did lights out of these pixels, which were three-dimensional blob wall bricks. And Aaron said I couldn't bring it, I had to do something new. And he said, well, why don't you do the toys? So I went back to the toys and came up with these furniture pieces. So you can see each one of these toys gets points and covered in baby powder and scanned into a digital model. And then those digital models are arrayed in configurations on the computer, and we find their points of intersection, like with the bricks, and cut them, and then assemble them. We did a duck table, which were German ducks. Every country has a toy that's important to them. The Germans made the ducks. The Italians did the eggplants. These are by an Italian company. These are an American company. They're whales and dogs. And during this time, my wife kept saying, these should be fountains. And I didn't understand why she kept saying they should be fountains. And then we were in Rome together with her Bernini Scholar parents and looking at Triton's fountain, and I realized why. It's because a fountain is typically an assembly of disparate figures, where like a sculpture might be two figures on a plinth. The fountain here was, I believe, 4 turtles with 4 dolphins, and each pair of dolphins holds a key, and then on that key are 4 shells, and then on the shells is Triton, and then Triton's drinking from another shell. So there's like 9 or 10 figures all piled up into one mega figure. And so for the Hammer Museum, we did the first fountain, which is, I believe, 44 whales that make the pool, and then these sharks, which then spout the water. And you can see they're built the same way. We used a bunch of blob wall bricks to make the bases and the plinths. And this is one that we did for ourselves, getting craned into our house. We're doing one down in Rio now, really big one. But anyway, that's a kind of logic of plastics in terms of bricks and masonry. Okay, but now to get to composites, in time for you to get to the game, I'll talk a little bit about some of the principles of using these surfaces. And for me, it's really become a kind of minimalism in the sense of eliminating or minimizing details. So the things that I try to do are reduce the number of components, try to use objects for more than one task, and integrate hardware and equipment into surfaces. So the details don't resolve things. The details are really about curves and ergonomic shapes. And it came out of working with Alessi and Vitra that I developed this idea. Because you can imagine, if you go to Vitra and say, I have a new idea about a chair. I have this amazing parametric computational power. And so we noticed most of your chairs are built with 15 parts. Now I can come and design a chair that could be made out of 15,000 parts. And every one of those 15,000 parts intelligently knows where the other 14,999 are. Like, that'll be a very short meeting, because they don't think that's innovation. If you go to Vitra and say, your chairs are made with 15 parts, I can do everything your chairs do in one part, then you'll take over the furniture industry. So there's an energy now in architecture to try to make things complicated because we can make things complicated. And I think in manufacturing, there's not a lot of interest in achieving complexity for the sake of complexity. So when I did this T-set for Alessi, the only instructions I got, other than a history of success and failure, which Alberto takes everybody through, was he said, it has to hold hot water or hot liquid, and it has to have handles, because architects never put handles on their coffee sets, and the only thing I ask you to do is make handles. So, and he said, you have $70,000 to realize one. And the way you'll do it is you'll give me your geometry. I will make a model of that with a 3D printer, and then we'll give that to a room full of people that will make it in sterling silver by hand. And that's how we'll do the sets. And the group, there were 25 architects that did this. Everybody did that. They did it in sterling silver. But I said, could I explode titanium if I can do it for $70,000? And he said yes. And so I actually looked back then, we had these telephone books. I looked in a telephone book for exploded titanium and found 3 numbers, and the first one was called high-tech welding, and I called them, and they made it, which is a great thing about Southern California. So the way this works is there's a vessel inside, and then there's a skin on the outside, and the skin is textured by capturing the tool path of the graphite mold, and the two things are bonded together with glue, with silicone. So you can grab it anywhere and you don't burn your hand. And all the handles become the part of the surface, and the volume is all held in the flask. So the entire pot is done in 4 pieces of metal. And all the information is put into those 4 pieces of metal. And I was asked then to do the tray. I forgot to do the tray. And the tray we did with one top surface, which captures the vessels. They all sit neatly in it. And then the bottom surface, you can flip over, and it has all the corresponding curves of this. So you can then turn the tray over and lay the pots down, and they open up like a flower. So six surfaces were used to make the entire thing. We commercialized that with these ceramic cups, which is all handle. So you can grab it anywhere because it's hollow, but you don't have to put a mechanical handle onto the cup. With Vitra, the ravioli chair is the same idea. There's more than 2 surfaces here. There's 3 different kinds of foam molded into the arms and the seat and everything, but it's one soft surface and one hard surface. So instead of legs and attachments and all these things, it just gets integrated into the ergonomics of the curves. So this kind of a language of putting ergonomic information or construction information into the logic of the surface, and building some of those surfaces in composites and in plastics. I mean, this is a conference room we just finished a few months ago that's all built in vacuform, sandblasted plastic. What I realized, it started to make things like very light and very minimal. This is a view of Osplin's chapel at the Woodlawn Crematorium, where he took a lot of the bent ply furniture he was making and used the same plywood and the skin of the interior and started to integrate the bent ply furniture into plywood panels. And so when I started the design of the Bloomhouse, which is in Southern California, I thought, like Osplind, I would try to take the logic of that Vitra chair and build all the interior surfaces to absorb all the equipment from the house. So in plan, you can see the hearth, the powder room, this like home office, the breakfast nook. It all gets absorbed into the walls of the house. And the same thing with the section. It's a loft. I mean, it's really a one-room living space, but I tried to make that living space very cozy or Heimlich by deforming the walls and deforming the ceiling. So this is a big, it's a little bit smaller than my boat, but it's pretty much a boat size hull that's bonded to the ceiling as a giant light fixture that also kind of brings the scale of the room down. And then the windows are all, these are stock windows. They're called cathedral windows. Like if you imagine a rectangular base on this, that's a typical detail. We just flip the head down as a sill. And so the windows also pinch together along the facade. So here's some photos of that, but the character of it was to make this very comfortable but continuously open space by undulating all the surfaces. So, I mean, here you can see where even the mechanisms like the heart, high precision from the computer manufacturing with a level of craftsmanship in the construction, which the logic brought to it. The other thing is the laser cutter we used was almost 30 years old. So it wasn't like a new technology, it was just nobody ever came to the laser cutter with a file. I mean, they'd been laser cutting stuff forever. It was just the contractors that would go talk to the laser cutter. They never had an architect come and say, you know, we want to cut all this stuff. So anyway, it was totally old school. You could have done this exact same project at least 25 years ago, and we wouldn't have had to pull a plaster out of retirement. And a lot of the furniture was also made in Corian, like this breakfast nook. The bathrooms are all, like the sinks are stock, but the cabinets for the towels and the toothbrushes and everything and the whole cabinet here, they're all pulled out of the walls and molded. Okay. The question about could you do two different materials in the same head, I think that's maybe not the question. The question is, can you do multiple materials on the same mold? This is a lantern we did with Bill Chrysler, where we have to make the mold. And then on that mold, we scribed the material transition between concrete and chopped fiber composite. And then we specially cut these wavy stainless steel rings to fit that surface. And then they laid up all the fiber reinforced concrete first, and then popped those off, and then laid up all the translucent chopped fiber, and then glued it all together into one final thing. And for me, this experiment in multiple materials on the same mold, this is some jewelry that uses the exact same logic of different materials on the same monolithic surface. This is for Swarovski. This is a museum in Santa Fe that does an aggressive renovation of its facade every 3 years for a major show it does. And we did these elements. It'll get repainted in a couple years, but these elements will stay, you know, for forever, or for as long as they want them. But on the exterior, we took all the doors and windows and made these composite scoops that cover them. These are models of kind of how those elements work. And then 4 of the scoops that are on the inside travel with the show to different venues. And part of the reason about this is I'm really burned out on building something for some special use that's temporary and then throwing it in a dumpster. So for these, we tried to use a material that was durable enough that it could be outdoors, but also that it could be reused. So it'll be used by 3 different museums, and then when they're all done with these 4, they go to a ranch in Texas, and we put them together into a little kind of a picnic place in the desert. So this is how a couple of them go in Minneapolis. This was just Friday. I mean, what these guys don't realize is they could have just picked that thing up and carried it, but they rented a crane. I think that weighs like not even 50 kilos. But these are a few of the pieces. That's one kind of just fitted. That's them fitting it into the facade. And I think we designed and built these in a little over 5 weeks. So it's the other nice thing about composites, it can be quick if you design them for who's going to build it. Bill's already talked a lot about load path, but I think what's important for everybody here to think about is that load path kills the geometry of your form. Like some designer gives Bill, Bill's designers give Bill a shape. Because of the finite element analysis he does, the actual structural frame of those millions of fibers doesn't follow the geometry of the shape. It follows the loads of the structure. So for the Swarovski sails, we used an existing sail shape because we knew we could mold it and played a little bit with about where the fiber placement would be. And you can see here the crystals are embedded in the sails, in the membranes. Thankfully, Swarovski has also a computer that places all those crystals. So they have for their like fabrics business, a computer that'll place whatever crystals you want in whatever design you want, like a butterfly for a jeans jacket or something like that. But so they would give us A2 sheets of crystals, and we could also play with the colors of those crystals. So there are like, I think we used 5 different colors in these different gradients that would move across the surface. And it was it worked. The frames are rolled aluminum tubes with then carbon bonded onto them in different layers to stiffen them up. Okay, that led to this chair we did for the Art Institute. For me, what's a revelation about the chair is that I've always hated tensile structures, but I've always had to work with tensile engineers. So like the Korean Presbyterian Church was engineered by a tensile structural engineer because of the complexity. And the engineer was always trying to tell us to make things in a fabric shape, but when you use a fabric, the fabric can only have one form, and that's whatever its hanging form is. So the same thing, if you use that kind of a structural engineer, they're going to always want to make everything into domes, which are like catenoidal domes, which are the optimum load shape. What's nice about Bill, which I realized, is he doesn't care so much about the shape as long as his mold can shape it. He's not always saying there's an optimal shape or we're form finding or there's an ideal shape. all he does is puts more structure where you need more structure, and you can get any shape you want. So for the hanging chair, we built this mold, which was really about the ergonomic comfort of a hanging chair. So this inflection point, we built into the shape of the chair, same as this inflection point. So if you look at a hanging thing, it's just always sad. I mean, it's always hanging. Whereas this is, got an inflection to it, which just gives it more visual activity. Also, these steep pulls and stuff you could never get in a fabric. You would get a thing that goes flat and then curves in the middle and goes flat again. So we built the mold, same as Bill said. We had to by hand lay up all these tapes in different orientations. You could see our kind of high-tech laminate schedule. But it goes from about 3, sometimes 4 layers of this 3DI tape in the midsection of the chair to between 6 and maybe some of them we did 12 in the corners. And then we vacuum bagged it and cooked it. And then you can see that it's not like a hanging surface. It really is a compression shell. So when it's hanging under its own weight, it's working under compression like it was a chip or a shell. But then the minute you sit in it, your weight overcomes that compression, that it becomes this comfortable fabric. So it's a really amazing structure because sometimes it behaves like a shell and sometimes it behaves like a fabric. And in this, it really depends on how much weight you put on it. But you can imagine structures which could, in one single form, have shell rigid qualities and also fabric tension qualities. And if my wife ever found out you said my family weighs 1,000 pounds, she'd kill you. It was all architects that were in the chair. There were 3 architects and 1 kid that got us to 1,000, not quite 1,000 pounds. But it's super strong. It's even, I think, stronger than, I could have taken 10 people, because it wasn't, well, we blew up one of these sails, so I know when they go, they don't give you much warning, but it was strong, or it is strong. The other thing is the detailing and stuff is all integrated into the shell. So it's just a couple of really thin little spectra threads that are glued right into the laminate. Okay, now the crazy part, which is, this was all leading to me wanting to design a boat for myself, I guess, but I didn't know. But in the last year, maybe year and a half, I've been designing a trimaran with a naval architect who now I kind of have adopted. He's like working in my office and working on this project like super intensely and pulling in a lot of resources. This, and I don't know, Bill, if I ever, or if Fred has shown you this, but this is a computational fluid dynamic simulation of the boat we're designing with air and water interacting at the same time. And we've been told by the company that does this that nobody's ever looked at air and water interacting. Usually the naval architect will do the hull form. They'll have all the data of its dynamics, and all the dynamics get loaded and looked at with the sails, and they go back and forth. But this, we actually just put the boat in the water and let it go. And maybe I'll show you the avalanche of catastrophes that happened. This one, where it has boards that help lift it so it flies a little bit out of the water. And where you put the boards is one of the things that this is really good at. And you can see here the boards were too far forward. So the boat just kind of wheelied up and then slammed down. But every single run always ended in some catastrophe, because it was like you put a boat in the water with no driver and just let it go. And it always found bad things to have happen. But as we would run them, what Bill calls the design space, meaning the limits between height and placement of the rig, placement of the foils, shape of the hull, all of that started to converge more and more and answer certain fundamental questions. And the thing is, it was like the old days in the sense that that simulation took 60 computers between 5 and 7 days to calculate. So it was like when I used to do a rendering in the 80s and we would send a thing and go home and hope it worked on the weekend. This was the same thing, only it was 60 computers working, endlessly. So this computational fluid dynamics software is not interactive. I mean, some versions of it are interactive, but it's very intensive. So what you do is, instead of having your CFD window open on your window while you model, which is what we would all like, you get data back that tells you where surfaces are under pressure, like with pressure maps, or it'll give you streamlines and it'll tell you where you're getting turbulence and vortices. And so based on that information, like this, I apologize, Bill, I know this is embarrassing, but hopefully only you know how embarrassing it is. But like all of this stuff, the red, which is where wind was either shearing off surfaces in a way that it was rolling around and pulling, or where wind was slamming against the surface and we needed to put an angle there, all of the shapes were informed, I would say, over about 6 months with this kind of information. And so all of this stuff is me starting with a basic typology and trying to clean it up, and then coming up with ideas and then running it through a model and working with a naval architect and going back and forth. It wasn't like sending something into a box and having the box give you the ideal form. So anyway, all along the way, I was modeling to this kind of information. And these are just some of the, this is kind of the styling and the surfacing of it. All the people in the boat industry think it looks like a plane, not so much like a boat. The interiors of it, we decided to actually build in my office to get some working knowledge of how composites work. And the design of it is really different than most things because it's moving. And the fact that this will be at maybe a 15-degree angle, and that you're sitting in different, sometimes you might be sitting on the wall or needing to hold on to things. And I was consulting with a boat company who told me when Philippe Starck did their boats in the late 80s, he asked them to put a boat in his backyard for the summer because he never had been on a boat. So they put a boat in his garden and they brought it in and they set it up, and he said, well, why is it straight up and down? And they said, well, that's how we store boats. And he said, well, put it at the angle that it sails at. And so they put it at a 15-degree angle, and then he slept in it for the summer at an angle. And I thought that kind of intelligence is really something interesting, that you really think about this thing not as a stable ground, but as a thing you live on the walls of. The reason I say that is I'm just starting a lab with UCLA that's all about moving buildings, and it's all about interiors that roll around and living on surfaces rather than standing on floors. So anyway, those interior elements, we're really trying to play with the fabrics. So the inside of the boat will all be just clear-coated fabric of carbon with some patches of Dyneema. And then all these elements we're building, like a king-size bed and 2 couches and a little kitchen and a head toilet. So because this guy Fred is in the office, the naval architect, it's all about weight. So every one of these things we make, which I'll tell you, this was the first thing we made, and we made it in a day. And now one guy is making 2 of these a day. It is so easy to do. Like the people Bill was talking to today, you should take your glue guns and your wood sticks and throw them away and make some foam molds and start laying things up yourselves, just like in your models. It's super easy. So we cut a foam mold and coat it. Then you just lay the cloth in, you put a foam core in, put it in a little vacuum bag, and this is not cooked, so you don't have to build an oven for it. And you could see this is a shelf that we engineered to hold 300 pounds, and you can see it weighs like 9 ounces, 10 ounces, something like that, and it takes like a morning to make. So the whole inside of the boat is going to be less than 100 pounds, like a one-bedroom apartment that weighs 100 pounds. So, thanks. Sure. How do I teach? Form. No, it's a good question. Well, at the Angewandte, which is the best teaching setup I've got, because it's very much like the Staedel, only longer. I mean, historically, the students study with me for 5 years. And so what we'll do is each semester, I'll give them one architectural idea. Like this term, we just finished floors. So everything they did had to be shaped formally by changes in floor. So I gave them, first we went on a trip. We went to look at libraries. So we went to Berlin, looked at Sharon. We've been to Viborg in northern Russia to look at Alto's library. But we looked at historical precedent and kind of paid special attention to how they were modifying floors. We also went to Stockholm and saw Osplin's library and the Woodlawn Crematory. So we focus on precedent. We really kind of hone in on one idea like that, and then try to spend 12 or 15 weeks to become expert in that one technique. It only really works there because, the term before we did hypostyle halls, so they knew how to do columns. And the term before that, we did massive facades, so they knew how to do carved poche. So by the time somebody's done with 4 years of studio, they've kind of run through a whole gamut of topics, and also usually a variety of scales of project, and then they do a diploma, and they kind of have to pull it all together. But I usually teach in a real focused way. We also go visit manufacturers and talk about materials and construction and things. But I'd say that's less of a focus. It probably is more of having a critical attitude towards history and the discipline, and developing good design skills.
Do you think differently about when you do, you explained very beautifully how you approach taking about the surface in terms of materiality and composites. And of course, there are many different kinds of composites, different sort of material. And then there are also different contexts for your objects. So one thing ends up being a fountain. And then the architecture. So do you think you think differently about the surface as a design?
Exactly the same. No. I would never think about getting near something that would float without working with a naval architect. And I would never do furniture without a company like Vitra. And, Rolf Feldbaum and his team, you need that expertise if you want to step into those other worlds. Well, you don't have to. I just saw Thomas Heatherwick's boat, which it's clear he's not working with a naval architect. But it's an interesting project. But I think if you want to have it be not high performance, because actually the trimaran's not high performance, the trimaran's just kind of fun, but it's not like bleeding edge fast or anything. But you need to work with somebody. and I really like to collaborate, especially when I step into fields I don't totally know. But usually that collaboration, I take much more out of it than I would get. So.
It's kind of, I mean, it's not a contradiction to your answer to this question, but the teaching is characterized in part by an enormous amount of discipline and specific purpose.
Yep.
So now I assume that it's also not just a specific architectural core.
Yeah.
With respect to the surface.
Yeah, well, it's also with the Angewandte, and you know, I assume it's in the atmosphere. You know, we're right next to Erwin Wurm, or you know, I mean, we're in a school with fashion and design and media studies and all kinds of applied arts. So I assume it's in the air, and also, you know, I show this stuff to the students. I assume they know it's in the air. But I would never teach like a jewelry studio or something like that, you know? So, I mean, not that jewelry's bad, but I just don't know anything about it. So, and same thing, I would never teach a furniture studio because I don't know anything about furniture. I mean, when I step into those spaces, I need to be with somebody and bounce back and forth off of them, so. Yeah. Yep.
Knowledge. So, did you change your mind in the meantime? And I know looking at the presentation, it seems that most of your research actually is back in other disciplines.
Oh, no, I don't mean that. I think architects just give too much away. I mean, if in the 70s, architects and artists were like working with each other all the time. I mean, literally working with each other. Like, I mean, you know, Frank Gehry's cardboard chairs were being built by young artists that would later become much more famous than Frank Gehry. And there was that give and take. I mean, like Tom Sachs and stuff like that. So the real exchange like that, I think, is the best thing. I think what becomes sad is when architects in 2012 say, I'm really interested in minimalist art, and they go back to that period when art and architecture were really talking to each other and just do it as a style. Like just do Donald Judd as a style of architecture. To me, that's not, it just doesn't have any integrity. I don't know how else to say it. It could be beautiful, I mean, could work well, but it doesn't have any originality or integrity. So, no, genuine collaboration is where architecture has to be. It's really not about like somebody copying architecture or architecture copying fashion or something like that, but it's about genuine dialogue and discussion and collaboration. I think that's the only way anybody moves forward. But the minute you start to copy a style or copy a period or have a style, that's when things get, for me, that's when I get scared. But I mean, it's also, you know, blob architecture and all that kind of stuff. You know, I hate that stuff, but it's how a lot of people understand things. I know that's the first thing everybody wanted to know is, will every house look like this? That was, every journalist would ask me, is this what the houses of the future will look like that we'll all live in? And it's just like, you know, I don't even know what that means.
Thank you so much.
Okay, yeah, you got a football game.